Okay.
Sir,
Yes, Kapil.
this is regarding the MCSV assignment.
Tell me.
What I have done is I have written a code for generating counterexamples for EF, AG, EU, and AR. Is it
Okay.
fine? Is it fine?
Yeah, so there is one instance for each of them, right? R, U, and G, and F. Yeah. So
Yeah.
that kind of exhausts the whole thing, isn't it?
No, I haven't
I
done
guess
ER. I
EEG.
haven't done ER. ER and EG.
That's okay. Yeah.
Okay, that's okay, right?
Yeah.
Okay.
Is it working?
Yes, sir, it is working.
Um, okay, I think I'll start in a minute. I'll go for one more minute to see more people. Okay. Share. Okay. So before I start the topic of the day, which is simplex, just wanted to take stock of things. So here is what the grade distribution I had proposed in the beginning. Okay, so I'll generally stick to it. As per this, there is a quiz or an exam, 25%. And that's what I want to talk about today. Okay. So we have covered, uh, some parts. So the quiz, what I'm planning to do is to have those. It'll cover the what I call as the theory part, okay, of SMT. Namely, as we started with discussing CDCLs at solving technique, then SMT logic, SMT solver internals. Specifically, we looked at congruence closure, then a combination of theories, DPLLT, and today I'll be talking about simplex procedure. And next class, the plan is Madhukar will cover this special purpose procedure that combines decision procedures that come for linear arithmetic plus the ReLU function, which you can do using DPLLT plus simplex as well, but that is supposed to be a more efficient one that tailors it to this combination of ReLU and simplex. And that is pretty much what we want, what we had planned to cover, or at least, I mean, there will be other lectures we might devote some part of it to discussing about project, and there are some topics that are still there. But as far as this 25% final exam or quiz is concerned, these are the theory part of SMT that I will be having questions on. Okay, and I want to schedule that during this last week, or yes, the last week of November. That is 23rd through 20, maybe towards the end of it. Maybe 27th of November. I mean, the questions will be mostly some problems, trying to check if you have paid attention in the class and understood some of those algorithms, procedures, and the concepts that were introduced through mainly giving you some, having you solve some problems. It'll be, I'm imagining, maybe 2 hours, at most 3 hours of quiz, where you will be, I will put it on Moodle, and you can, you're given whatever time that we decide, 2 hours, 3 hours, and after which you will submit it on Moodle. So that's what I'm planning. So is November 27th? Okay. Okay. Firstly, any questions? And with the date of November 27th, is that fine?
It will cover everything till then, or?
No, as I told you, this is, that it'll cover simplex and ReLUplex. Okay. That is
Okay.
subject matter for today and the day after. After that, anything that we talk about may be something of general interest. There are a couple of papers that we thought that might be of interest to cover with regard to verifying complex systems.
Sir, you'll be uploading the notes, right?
The notes about what? Notes
About the DPLL and the
I mean, I have already uploaded. I usually am fairly meticulous about it. I upload it, if not on the same day, the next day. Okay. So if there is something missing, then you should. I mean, the last time I checked, I have uploaded all of it. If there is something missing, then I will check, and you can also check. I mean, I've been fairly diligent in uploading the videos as well as the class slides. Okay, if something is missing, I will also check. I encourage all of you to check and to see if something is missing. We will definitely upload it.
And when will be the project submission due?
That okay. What? So that's. So we were planning on after the submission of proposal, which will be reviewed and evaluated, for each of you to give a brief presentation, maybe 15 minutes or half an hour, no more than maybe 15 minutes with the demo and of your results. So that is something that we were planning. And but if you have the submission date, okay, Hitarth, do you have any suggestion? So I'm okay with you submitting on the last day. See, technically, what is the last day of the term? 27th, isn't it? I need to know. I mean, is it okay if we had 27th?
Yeah, I was of the opinion that Madhukar here. I was of the opinion that they could be given a couple of more weeks after 27th. 27th, I think, is when the teaching ends. The end sem, the semester, I think, ends when the end sems happen, and that will be another week from then.
I will check as to when I know that we started 2 weeks late. So I think that should be possible. I will double check on when the grades are due. So we need some time. I'm okay with giving, but there is a deadline for grades. Okay, I'll check with Madhavan on that as to when the grades are due, and usually then. So let's suppose that, so what are you proposing then? That you will, so if not the 27th, give it 2 weeks. I mean, that is, okay, say if I give 2 weeks, then it will be December 11th, correct? And then we will take another week to, so maybe they can, yeah, so to grade, then by that time it will be December 21st that we will be, well, I'm not sure if they'll wait for the grades, that part. I have to check, okay? So that will be one constraint. Maybe giving till, yeah, December 11th. 4th should certainly be possible. But you think that since everyone worked on the proposal, etc. So maybe I'll we can do tentatively, but then yeah. So everyone should be available. So if you want them to give some brief presentation. Okay, that we should certainly have. Then, if that can be done during the week of, say, like 14th or so, okay, early 14th should definitely be possible. I will check on the due date for grades, and then we can decide, on that. But if we do that, then everyone should give a commitment to be available for. Because it will be very difficult to grade the project without some presentation about what you have done, what the code is, seeing how to run the code and the results. If you go away and not available, then it will be difficult. So, how do people feel? I guess, would you rather have those extra week or two?
Yes.
Okay.
Yeah, it would be nice if it's in December.
Yeah. So if that's what feel, I will check with Madhavan, and then we can decide on that, on the date and the schedule for making your presentation accordingly. I will check with Madhavan and.
Also, sir, which book are you referring for the theory?
Yeah, so this is the one which is, I think it's uploaded on Moodle. Okay, I mean, I did it even before the first day of class. That, and for simplex, pretty much that book. Okay, and I've also given you the various chapters, and I can refresh that, okay, as to what the various things that I've covered and so on. I have not written it up now. So that's the book. So it's on Moodle. Okay, there is a link, I think, to that's been shared. Haven't you, Siddharth? That's been done, no? Siddharth, are you there?
Sir, I couldn't find the book on Moodle.
Not, is it?
I can only see the book by AWS.
The book by who?
AWS, someone, OS, I don't know.
Oh, the decision procedure book is not there, and you're not. Oh gosh. So which means people, I've been referring to all these things, and then
So Moodle is slow sometimes.
Oh, yeah, that's okay. I don't need that. I think I'm pretty sure that thing is there. It's not there, huh? Decision procedure book. I remember some link to that book. So otherwise, I will upload it. I mean, it's a bit surprising that I've been referring to that book, but no one to this day has even looked at it or has reminded me of that. Okay, better late.
It's available online.
Is the information about its availability online posted on?
You mean Cronin and Streakman, right?
Cronin and?
Streakman, right?
Correct.
Yeah, it's available online.
It's available online. You checked it on your own, or is the link or some information about it is available?
It's not in Moodle. I checked it on.
Okay.
The edition might be different. That's what I'm worried about.
No, but that won't make a difference. Okay. That won't
But
make
in
much of a difference.
MC,
Yeah, but
model
it's
check,
not linked in the Moodle. The Moodle page
Okay,
just
so
contains the
that is
AWS.
something that, okay, so that's my mistake.
sir, for model checking also the book I found it online, but the edition were different, and the books that the link you gave is significantly different from that book.
Zubin is here. Zubin can answer that. Zubin,
Yeah.
there is some claim being made
No, sir,
here by
it is
Kapil.
resolved actually.
Something was not available. So I know of only edition 2E. And I think that we had, you had uploaded
Yeah,
the,
that's on Moodle. Yeah.
that's
That's
on
Moodle.
Moodle.
Yes,
Okay?
it's resolved. So it's on Moodle now. But I found out the book, it's the same book online, but the edition was different and the book's content are
But
significantly
that's, yeah, but that's not my problem. Okay.
yeah.
So I had made a login and user ID and the password available to that for the latest edition.
Okay, yeah, yes, sir, no problem.
Yeah. Okay. Yeah, but this one was a mistake. Okay. So I thought I had it, but I'm not sure. There's an e-textbook so which we messed up, Hitar. Okay. So these are some things that I would like, some reminder, someone to do, at least remind me of that thing. So that's a mistake. I apologize, and I will make sure that that thing will be available. But the thing is that have I given you a cover for the thing, or
Sorry, could you repeat that?
no? Had I at least even given the cover for details about the textbook?
You mentioned it in class sometime, but it's not in Moodle.
Okay, I'll make sure that I will put a link. See, I have the PDF. Okay, maybe the PDF is available online, but I can't upload the PDF. Okay, that's too big. So what I can do is do something similar. Hitat, if you could take the initiative. Hitat, are you there? I guess Hitat is not there.
Yeah, but I'll take the initiative, sir. I'll...
Yeah, what you have to do is to take like what Zubin has done. At least put a link to say a Google Drive or something like that. Yeah.
Yeah, certainly. I'll make it available for. I'll do it today itself.
Okay, thank you. Okay, so I'll start with this. See, this thing. So, how many of you have seen Simplex? By the way, this is after a long time. I mean, that I'm covering Simplex in this SMT. I usually cover other decision procedures that are relevant in the context of programming languages. So you must have. How many you have seen? Because some of you might have taken optimization course. There are several optimization courses that are offered here at CMI. So have you, some of you seen Simplex before? How many of you have seen?
Yes.
Most, yeah. So most of you have seen, you could say that. If there are some people that have not seen Simplex procedure, how many? Yeah. I'll cover it anyway.
Sir,
I
I
have not seen it.
Okay. So there are some. And there are some people who have seen it. But there is, there are some not variation at the core, but the requirements for using it as a theory solver in the context of DPLLT will sometimes make it. Add some more requirements, that there has to be some incrementality, and then it has to give certain information in a certain way that DPLLT can use. So the theory simplex procedure that are integrated with SMT solvers, they usually have take care of these additional requirements. Okay, so to see that, what I mean by incrementality, let me go back to how DPLLT uses the theory solver. Okay, so for example, so this is here, it's linear arithmetic with some Boolean combination. So after you make assertion, so as you know, so it makes literals out of all the these atomic literals are the ones that are asserted as Boolean abstraction, Boolean literals at the DPLL level. Okay, once there are a bunch of partial assignments to here each B1, B1, B8, B6, B5, they are all linear arithmetic atomic literals. Okay, so all of them, as you make these things, assert these assumptions, you need to check. Okay, one of the things that you need is you need to check if you could infer some other theory literal, in this case arithmetic atomic formulas that occur in the formula, in the original formula that you're trying to solve. So if you could infer any of those things, that is what is called theory propagation. Okay, therefore your simplex procedure will have to be able to have the feature to give these these implied atomic formulas. Okay, that is one. And after that, okay, so there is theory propagation, which is part of DPLLT. And then once you have the detection of whether there is a conflict or not, see, this conflict is not exactly at the propositional level. It is actually once B2 gets implied at the propositional level, there is a conflict, there's a theory conflict. Okay? So anytime, so you will be incrementally, so DPLLT will be, as you generate partial assignments, it will be incrementally asserting atomic formulas into the simplex procedure viewed as theory solver, and it has to both give, when on demand, maybe literals that are implied by it. Okay, and if once certain number of assertions of atomic literals are made, you can check if there is inconsistency, then it has to report that. And in addition to reporting that it is not, that is unsat, it has to give this kind of explanation, okay, of why it is unsat. So here, not of B5 and B8 happen to imply not B2, okay? So this is as a result of unsat. The clause 8 was as a result of sat. I mean, as a result of, that it was still not, so when it was still no inconsistency was detected, you generate these things, okay? And that can be done on demand, but certainly this one will have to be detected, okay? And then the explanation has to be given, okay? So what I'm saying is there are some requirements. And also the other thing is that general simplex, when it is used with optimization, usually has an objective function that is given in addition to the constraints. And it has to maximize or minimize the objective function. Whereas for us, satisfiability, since we're interested only in the satisfiability, there's no there's no objective function to maximize, minimize. So those are some of the differences, and that is what I will be also illustrating of when we discuss the simplex procedure. If some of you have seen it and you want to chime in as to what you want to add your thing, feel free to do. Okay. So here it is. Yeah, this is chapter 5 of the textbook, and the textbook itself is based on this paper by Bruno. I think it's a very well written paper. So I kind of, before I prepared my slides, I reviewed that paper, and I've added some things from there. I will upload this paper as well. I mean, you could read it. I mean, I think in some ways it is better than the book chapter in my opinion. Okay. Yeah, and also I want to make a brief digression, to history. So even if it means that I can't finish the simplex procedure, it's okay. So history. So when maybe some of it I've given you. So history of SMT solvers. Okay, so SMT solvers, I might have mentioned that they were developed primarily in the mid 80s, 1980s. Okay. Yeah, so that was when they were developed, when interactive theorem provers were being developed. Okay, there was a lot of interest in program verification, and to automate or mechanize those things, to mechanize proof development and proof search. And yeah, so in that context is when this was developed. A lot of the work happened, so the leading groups were, one was at Stanford, which is where Nelson and Arpin were doing their research at the time. And there was also a very well-known computer scientist called Zohar Mana, okay, so who's very well known in doing program verification and so on. So there was one project there called the Stanford Theorem Prover or Stanford Verifier. So there's a lot of research there. Simultaneously, there was also this place which is now called SRI International. And it is, at that time, used to be called the Stanford Research Institute. It was an institute that was set up in Menlo Park, outside of Stanford, primarily to do top secret research that you couldn't do as being part of a university. So there's a lot of collaboration between Stanford University and SRI. And several of the there was also a theorem proving project there in the context of application to fault-tolerant algorithms. Specifically, there's something called Byzantine fault-tolerant algorithms. These are protocols to mask malicious faults as well as all kinds of faults while executing this protocol. That was a very big project, funded at SRI, and there were people there like Boyer, Moore, who are very famous in having developed one of the earliest and very widely used theorem prover. And there was also another theorem prover that itself was being developed at SRI, mainly for applying it to Byzantine fault tolerant. By the way, Byzantine fault tolerant at that time was started as somewhat of a challenge problem, and there was some interest in verifying this protocol for military applications. But now there is so much renewed interest in applying it to Byzantine, because in the context of blockchain verification and so on, that Byzantine protocol verification has come into vogue again. And companies like Facebook, Google, and lots of other companies that are actually interested. And there were a couple of people at SRI, Pease and Shostak, okay, who were also simultaneously developing. Their motivation was to have these SMT solvers, these decision procedures, as backend to theorem provers, so that mundane proof steps could be discharged automatically in the process of proving more complicated things. So both these groups, and now later there were several SMT solvers that were that came about, and CVC4 is one such open source software. I mean, speaking of SRI, that research is still very much being done by in the computer science lab of SRI. And Bruno is leading that group. There is among the top performing SMT solvers, there's one called YICES, YICES, and that is architected and built by Bruno, which is integrated with a theorem prover called PBS. And Bruno is still at SRI, and he heads a group that does. And Leonardo used to be at SRI, but right now he's at Microsoft Research. And these two people have done a lot in the development of ISIS and integrating these decision procedures. So this particular paper is written by Bruno and Leonardo. Okay? And I'm just saying, SRI is a good place if you're interested to intern and so on. So if you're interested in doing projects in this area or in theorem proving, and so they also do machine learning, applied machine learning for building theorem provers as well as for verifying machine learning algorithms. So if you're interested, you can get, we can talk, you can get in touch with me. So that's a slight detour. Oh, I was talking about CVC4. Now, CVC4 is another leading SMT solver. It has the unique distinction of being an open source SMT solver. Yeah, ISIS and their Z3 are freely available, but their source code is not available. Whereas CVC4 was built as an open source and open architecture SMT solver. And that was also developed at Stanford, okay, as a small project in the context of application to hardware verification, okay, specifically microprocessor verification. They took parts of the Stanford verifier that Zohar Mana had developed earlier in the context of program verification, and then they took parts of that and they started applying to microprocessor verification, and then it grew bigger and bigger. And and the person who was in charge of that was one David Dill, who used to be a professor at Stanford. Maybe he's still part of it, but now he works for Facebook. David Dill. One of his PhD students called Clark Barrett. So that's who took this thing and developed into full-fledged general-purpose open source SMT solver. And then after his PhD, moved on to New York University, but he's back at Stanford. So the research for CVC4 is back in Stanford, and it's and it's being done by Clark Barrett. So that is so CVC4 is being developed there, and there's a lot of development activity at SRI, and these are probably the two big places other than Microsoft Research where these state-of-the-art SMT solvers do get developed. Of course, there are other places in Europe that do develop. There's something called MathSat. I don't know which university it is there, and a few others. They all compete in this yearly SMT competition that that happens. So some of the SMT solvers that I've mentioned, like CVC4, ISIS, Z3, etc., they are all medal winners at that competition. Okay, so here is the logic. So for the thing, there are arithmetic terms, linear terms, and inequalities, and strict equalities, equalities, and they're all conjunction of formulas. Okay, so it's a conjunctive fragment of linear arithmetic. So simplex is one of the oldest algorithms for numerical optimization. So the input is what is called a linear program, a conjunction of linear constraints over reals with rational coefficients, along with an objective function, as I mentioned. The output is an assignment beta to the variables that maximizes the objective function, such that all the constraints that are given are satisfied. See, simplex is exponential in the worst case, but there are things that are much more efficient than simplex. One such thing is called ellipsoid, but the most practical implementations and most existing implementations, even for optimization, and certainly in SMT solvers, they all use simplex procedures because although its worst case complexity is worse than some of the other existing algorithms, they outperform them in practice on an average, and so therefore simplex is still used. So as I mentioned, how are the requirements on simplex different for use with SMT? By the way, before I move on, is there any question that you have about the history rambling that I made about verification, SMT, and the thing? Yeah. Okay. Okay, so as for simplex in the context of SMT, we only have C. We're only interested in the satisfaction problem. It must be incremental, as I explained. And once there is unsat, inconsistency, it has to provide explanations, and it has to have support for theory propagation. So the first step in simplex is this equi-satisfying step, much like, remember that how the combination theory solvers was done, okay? So, when you had, before equality propagation was done, so we kind of introduced extra variables to purify all the terms, okay? I mean, terms were made to be introduced new variables and equated them to all the terms, non-variable terms that occurred in the original formula, and then added these constraints so that eventually what you had was you could deal with only elementary atoms, which contain only variables, okay? And you could, in that case, propagated equality only over variables or disequalities over variables. So here you will be then reducing, by adding additional variables, reducing them to constraints, equality constraints over just variables. And that's the transformation that's done. So here is something which is not a conjunction of formulas, okay? But yes, it is arbitrary, although simplex itself is for the conjunctive fragment. So I will illustrate this equi-satisfying pre-processing step on an arbitrary formula, okay? An arbitrary linear arithmetic formula that has an arbitrary propositional structure. So you look at all the non-variable terms here. So here in the formula, there are two terms, right, that are not variables, x plus y and x plus 2y minus z. So you introduce two new variables and transform phi into a formula of the form phi a and phi prime. So phi a is a set of equalities between the new variables that have been added and the term that they denote, okay? And the function terms that they denote, as here, x plus y and x plus 2y minus z. And then you replace those terms in the formula with the new additional variables, so that your constraint will be, all your inequality constraints will be on either the original variables or the newly introduced variables. And this is kind of can be considered as a normal form for LP satisfaction. Okay. So I don't know, since some of you have looked at simplex in the general simplex, I guess they also do this simplification, okay? And I think some of the new variables that are introduced there are called slack variables, okay? So maybe this step is done there as well. And some of you have looked at simplex in the context of optimization. Maybe I'll ask them, is this what I call as a purification step, variable introduction is done in general simplex also?
Yes, if for every inequality you transform it to a equality and new variable that is positive or negative.
Yeah, okay. So that is then, it is something similar here. So then you have, set of all the variables, good. So that have the original program variables or if you want to call them, and additional variables, each of which denotes a term. And yeah, so you have phi A, which can now be converted into vector of equality for 0. Okay, I mean you can make these linear expressions they're equal to 0, and then you have a bunch of constraints on the variables with, in general, some lower bound and upper bound. Okay? So a theory solver, the problem of what the theory solver has to satisfy, has to do, can be considered as a linear, which, through this transformation reduces to one of searching, value assignments to these variables, to all the variables, both additional variables and program variables, such that they satisfy a conjunction of variable constraints modulo this vector A of B having to be equal to 0. So that vector now is, there's one row for every equation that you have. So that depends on how many functional terms that you have in your original thing. And then, B is just a column vector with the program variables as well as the addition variables. And then you have these constraints, okay? If there's no, if either the lower bound or the upper bound is not present, then it will be assumed as either minus infinity or plus infinity. If some constraints are missing for certain variables, it just means that it can be anything, okay, between minus infinity to plus infinity. So you could, so what this theory solver has to do is to find an assignment to all the variables such that all the bound constraints are met, modulo these equations, denoted by A, B, have to be certain. So disequalities are apparently, there are different ways of handling it. If there is something in some situations I've read that there is zero detecting procedures that are used as substituting, and then you can add that to the simplest thing. But here, at least in the context of the description, we will assume that disequalities are just replaced by a disjunction like this. But of course, then they're no longer a conjunction of inequality. That's why simplex itself, if you want to solve it, they may have other methods such as detection, zero detection thing. But here, at least we give the theory solver only for the conjunctive fragment. And if you want to have disequalities, that can be solved in our case, at the DPLL T level. Okay, so so that is what most SMT solvers do. Any questions so far? So the pre-processing step is clear, I presume. Okay, so I said that there's, what are these specific, the typical API to an LP solver acting like a theory solver inside SMT. So, like I said, it has to be able to assert on demand an atomic formula, a theory literal. In the current state, kind of incrementally, okay? Usually the LP solver assumes that all the constraints are available a priori, and then you just check satisfiability. That is a mode in which the theory solver can be used as well. But typically for SMT, for the DPLL, these literal assertions come one at a time. So this can return as soon as these assertions are incrementally made. It can return okay, which means okay that it hasn't detected unsatisfied. So the checking for unsatisfiability can be done incrementally as well if need be. Okay, and if it is unsat, then it has to return a minimal explanation. That is like an unsatisfying assignment or a subset of the original atomic formulas. I mean, a subset of yes, a conjunctive subset of the original atomic formulas union the new assertions that you have. What is alpha? Set of tau is a subset of alpha. It has two, where tau is a subset. It returns tau. That's what it is. Okay, which is it takes in account all the assertions you've made so far and returns some minimal explanation. Okay, this assert itself may or may not do a full check. It doesn't have to be some thing, but because you can always invoke. There may be some quick checks for unsat it can do, so you can design it such that it'll just, does only certain cheap, very inexpensive unsat checks, okay, until it thinks that it has enough, accumulated enough asserted literals to do, and after which it can do a full-fledged, invoke the full-fledged theory solver on it. So, and that is done using the full-fledged check, okay, which really checks for satisfiability, unsatisfiability of the thing, and then and additionally, it can create checkpoints after it does a SAT. It can create checkpoints there so that DPLLT typically backtracks. Okay, so at wherever you have a SAT, you can make a checkpoint after every check when you've checked if it is SAT. If it is unsat, then of course you will give an explanation here and you're done. Otherwise, it can create checkpoints so that it can be used during backtrack, so that all the solver state, the theory solver state up to the previous checkpoint on the stack could be remembered, okay, so that they can be reused when you further extend your partial assignments in the concept of DPLL. So these are, so this is typically the kind of API that are built as wrapper around the core simplex procedure that are integrated into SMT. So then you have propagate, which is supposed to return these kinds of implications. Okay?
What is alpha?
Alpha is the the set of assignments that have been asserts that have been made up to that point. Okay, so you make assert, you keep on making asserts now, so incrementally, and then it's the accumulated series of asserts that you have atomic, literal asserts that you have asserted into the database. Okay, and then gamma is the new assert. So you can say that here in the case of assert, before this assert was invoked, there might have been a whole sequence of asserts. Okay, so that gamma plus the additional, earlier asserts. Okay, alpha denotes earlier asserts. That's what it denotes. Okay, so because a single atomic literal is always satisfiable. Okay, therefore so that's how it is done. So the inconsistency is on all the conjunction of all the asserts that you've made up to that point. So these theory propagation are valid consequences of the some subset of the asserts that you have made so far. Okay, if they happen to infer some new literals, gamma I in this case, that are part of atoms is the set of all literals in your original formula. Okay, in your formula that you're trying to solve at the DPLL level. Okay, so if it knows about, the solver knows about that, then it can infer any one of them on demand. It can then produce these kinds of valid consequences. So remember that when I showed you on the DPLL slide, that's what happened after asserting a whole bunch of atomic linear arithmetic literals. There was a theory propagation step that was done, and it was giving something like this. Okay, some subset of the literals asserted implies a new literal. Okay, it's something that you learn newly. So these are the something that interface. All these things, as you'll see, we need to be extracted as after you do this check. Okay, the outcome of check can be either sat or unsat. If it is sat, then it can do propagate of some literals. It can do either all it can check, propagate, generate as many literals in the original formula and then give it, or because that will be expensive, so sometimes propagate has to be done in a constrained, in a limited fashion. There are various strategies that are used to how extensively you do theory propagation. So after you do a check, if it is sat, then you do propagate. If it is unsat, then you do you ask for an unsat explanation. Okay, so these are something that are something that that you additionally require for a theory solver built on simplex. So therefore, there is some engineering that also goes into adapting simplex procedures to be integrated into SMT solvers. So I'm just giving you a typical, some insight into it. So, okay, any questions so far? Oh, okay. So before I show you the actual algorithm, the procedure, the pseudocode for the procedure, to give you an overview of simplex. So it partitions the, so some key ideas and key things that you need to understand about simplex. So it partitions the original set of variables into two disjoint sets. Set of what are called basic variables, or sometimes they are also called dependent variables, and non-basic variables denoted by n. So, and as it turns out, as you will see in the as you understand or follow through the follow the simplex procedures, variables in n, the non-basic variables, they usually happen to satisfy during the course of the simplex procedure their bounds, except possibly initially, and those in B may or may not. Okay, it keeps a partitioning of these two variables in the original set. And the constraint AB equals Z is 0 is itself maintained actually as an equality as it was shown originally. And this one is called a tableau, okay? And it's an equality relation between the basic variables. Every basic variables is expressed as a linear combination of the non-basic variables, okay? See, in the original case, we had the program variables and the additional variables, okay, that were introduced. So here, this is a different partitioning. So in the tableau, some, these, what we include in the basic variable could be both additional or original program variables. And so is non-basic, and they change during the course of execution of the simplex procedure. So here is an example. So this is the formula that you saw as an example. So where you had introduced the additional variables and you had these constraints over the variables. So this one, I showed A by actually moving it in here and then expressing the constraints A of B of Z. So just this equality simply, if you just keep them as is what the tableau is, okay? And we will write the tableau in this fashion, not in an table fashion. So the rows of T here, S1, S2, they are the variables, the current basic variables, and the columns are X, Y, and Z. Okay. So the ones, so the left side of the equalities here are the variables that are considered to be as part of the basic variable. And on the right side, so sometimes I call them as columns because X, Y, and Z they're represented as columns, and the coefficients are corresponding to them as they are written. So you can visualize them as typically sometimes tau is given in the book, at least in the textbook, it's given as an array, as a table. But it is the paper, it is written this way. So I followed that notation. But you should be clear about what the basic variables are and what the non-basic variables are. Okay? In this case, the basic variables happen to be exactly the additional variables, and the non-basic are the program variables. Okay, usually at the start of simplex, that's how Tableau is. Okay? Any questions? Okay. So what simplex does is it chooses one variable in as I told you that these are these S1 variables may not these rows, the S1 the basic variables, they may or may not satisfy their bounds. I haven't, so the bounds are kept here, so they may or may not. So if there exists some row, a basic variable, which does not satisfy one of its bounds, then it chooses one such variable and it makes it satisfy. It looks at Y based on the current assignment, okay? There is a current assignment to variables as well with some initial assignment. So the violation of the bounds is always with respect to a current assignment. Okay? So this is one check it does, okay, to see if the current assignment, as per the current assignment, if any of the variables are, if any of the variables, X variables are the basic variables violate one of their bounds. So if so, it picks one, okay? Then it does what is called a pivot operation. So you update the current, so you update the current. That's what I mean when I say you make it satisfied. So how it is done? It is done using using this pivot operation. So you update the current variable assignments, or beta. Yeah, so you update it to reflect the adjustment made. Okay. For example, if your current assignment was assigning 0 to all the variables, okay, here x, s1, and s2. S2 would be violated because 0 is not greater than or equal to 4. Okay, so that's what is done. And what it does is it tries to adjust, that is either pick one of the non-basic variables, okay, and see if they can be increased or decreased to make it make that S2 satisfy the violating bound. And when it does that, it does adjust it minimally, requires so to reach one of the violating bound. That's what it does. So the variable, I mean, it could be violating either the lower bound or the upper bound, and it does adjust the non-basic variable chosen. There could be several different possible variables that you can choose to make the adjustment. It picks one among the possible things, and then and the other thing is it adjusts it so that the S2 in this case will reach its violating bound 4. Okay, and for example, that can be done by, in this case, by increasing x to 4, okay, by bumping it from the current assignment, which was 0. And after that, you flip the make x, flip xi and xj. That is, you make s2 a non-basic variable, and x, which was a basic variable, which was a non-basic variable, to make it a basic variable. And when you move these things, when you flip it, you will have to eliminate the, in this case, x, if you had chosen x. And that's what flip the pivot operation also includes changing this tableau, okay, by eliminating the one that you move. Okay, so S1 is eliminated, and therefore you'll have to adjust it. So here is an example. Okay, maybe I should have shown this example itself. So with this assignment, that's what I was talking about. You have S2 violating, and so you can make X go to 4, and then you will have to make S2 become remove it from the B set and move it into the N set. When you do this, you do a linear transformation. I mean, so you will define X, and then you make substitute X. You have to eliminate S2 from the left-hand side here, and therefore this is what you do. So this transformation is equality preserving. Okay, so and then you update all the rest of the assignments as per the new assignment that you give for the adjusted variable, and you can plug that assignment to the variable into these expressions and get the thing here. So that is the pivot operation. Okay, and what you do is you repeatedly perform this. What simplex does is it repeatedly performs this pivoting operation until it hits a sat or unset. Okay. Yes. So at this step, if you see something being violated, and if there happen to be no non-basic variables that you can use to adjust to fix the violation without violating their own bounds. Okay, so then it is unset. Okay, if not, if everything is every basic equation, basic equation correspond, the bounds corresponding to the basic variable is satisfied, then you return set. But the important thing here is that you have to use a fixed ordering on variables. Okay, if there are multiple choices available in picking the basic variable, if there are multiple basic variables that violate their bounds as per the current assignment. So in this case, S2 happened to be the only one for this initial assignment. Otherwise, so if there are multiple assignments, then you will have to choose the variable that appears earlier in that ordering. Okay? Similarly, you have to, if there are multiple choices available among the non-basic variables to make the adjustment to fix the violation, then you will have to choose the non-basic variable that appears in the earliest in the variable order. Okay, so this is, I'll go through examples and so on, but this is roughly what it. This is the main steps of the algorithm. Okay, any questions? Okay, so yeah, this is something that, see, it helps to at least to see why this thing is working, to see it as a constraint solving problem in the Euclidean space. Okay, so each inequality constraint defines what are in the Euclidean space called half spaces. Okay, so these are all things. So, for example, in the two-dimensional space, two-dimensional space, each inequality defines planes, right? So, in multi-dimensional thing, you call them half space. Okay? So here the problem is that is shown here has two variables. So we are using two-dimensional space. So that's what these constraints, inequality constraints denoted by phi prime denote in the geometric space. And each equality defines hyperplanes, okay? So which in the case, in a two-variable space, it is these are lines. So a solution is defined by the intersection of all the half spaces and hyperplanes. So these equalities define hyperplanes, three in this case. So here you see there is these three lines that are shown here. And each of them is equated to S1 and they have a bound, okay? And these bounds, these inequalities define portions, planes, okay? So which are regular planes into two-variable domain. Then if you extend this to multi-dimensional, they are called hyperplanes. In three-dimension, for example, it is polyhedrons, okay? So, and the satisfying solution is the intersection of, the entire space of the solution is the intersection of half spaces defined by the inequalities and, and the hyperplanes, which are lines in this case. So that is the shaded region here, okay, in the thing. So it extends infinity. So, but there are extremities, those things, okay. So there where these boundaries, these lines intersect, okay. Any point here within the shaded region, including these extremities, these what I call as intersecting points, are solutions. Okay. So the satisfaction, you know, when you're doing the way I understand is, yeah. So you can pick anything here, but the method, this pivot thing method that I just now gave an overview of, concentrates on you know, picking these intersections. I mean, these points of intersection, which in the general case, they will, you know, they can be sets of you know, points. Okay, so for any, yeah, as for any finite number of variables, there are only finitely many such things. So the simplex procedure, the pivot operation that that I just gave an overview of, it picks these things and it kind of searches in a certain way by looking at you know, possible things, and then it converges to one of these two extremities, okay, which even in, as long as the dimensions are finite, because the variables are finite, there are only finitely many such you know, hyper intersecting points. So what the adjustment and pivoting operation that I just described does is, so it starts, the simplest procedure starts with some initial assignment, okay, to the variables, which is usually all zeros, so with A, and then it picks, so each basic variable denotes these lines, okay? So if you pick S2, say, as the basic variable, so obviously A violates S2 as well as S3, I guess. Minus x plus 2y is S3. 2x minus y is S2. No, it violates S1 and S3, correct? Yeah, it violates S1 and S3. S1 is the line x plus y, this one, okay? Here, I hope you can see my cursor. And S3 is this line that's going here. So if you happen to pick S1, and you pick S1 and X, S1 as the basic variable to the violating, to fix its bound, and choose X as the non-basic variable to adjust the assignment to make S1 satisfied, then you will move from A to B, okay? Because you will end up fixing S1. So, and you do it, as I mentioned, you do it such that you do the minimal adjustment that is needed to go to its bound, okay, which in this case is 2. So you move from A to B. So that fixes S1, and you flip S1 and move it to non-basic, and move X to the thing. But there is, yeah, that movement X still, you know, because there is the constraint on X is already met. The only thing in the non-basic thing, so you will flip S1 with X. So still 2x minus y. S2 is, no, S3 minus x plus 2y. This line is still not satisfying. And then what you do is you will have to pick that S3 to do it. Then you will move along this line and then move to C, okay? For and that step, okay? The second iteration of the pivot operation, in which S2 is the violating one, will will get you to C. So that's what is happening through this adjustment and in pivoting. So as you can see, the if you choose different orderings, yeah. So any questions so far? I hope this, for me, this was quite illuminating to see it as how it works in the Euclidean space. Certainly, it is hard to kind of imagine in a multi-dimension where there is a correctness proof in the paper, although it is not there in the book, which is a general argument for the thing, and I will give you intuition. But at least this way of viewing, I found it quite illuminating. So any questions so far? I hope you got some intuition based on what I just now described as to what exactly happens when I do the adjustment, okay? So the adjustment and the pivot, actually, the adjustment will move the point from A to B. And after that, once you flip and you move something to non-basic, any further adjustment will not affect any of the non-basic variables, okay? So that's why you are moving. When you move, you will still preserve the S1 constraint. And what you're doing is you're now using, if you're picking, then after that, Y to adjust to Y next, because Y is the only one that you can actually pick to adjust. Then you move to C. Of course, you could pick a different variable ordering. So if you picked, say, S2 instead of, no, S3 instead of S2 to do it, then what you will do is you will move from A to this negative side, okay? If you chose X to fix. There's also a solution which takes you from A to the left side where this minus X plus 2Y greater than 1 line intersects X. And then after that, you can choose to fix X plus Y greater than or equal to, which will make you move along this line and reaches C. Okay, so every different variable ordering will give rise to different sequence of pivoting operations, which will so there's but they'll converge on one of these intersecting points. They can also be a solution that takes you from A to this point too, and then converge on this point as well. Okay.
So how do we know whether it's unset or not?
How do I know if it is unsat? Okay. Now, yeah. So I kind of rushed through that. So at this point, if you have some basic rows, basic variables, which are violating one of their bounds, and when you choose the variable, the non-basic variable to adjust, you will have to either increase. See, when this is S2 is violating. Okay, so short answer to your question is that there's no non-basic variable can be whose value can be adjusted relative to its current assignment, such that you can fix S2 without violating their own bounds. Okay. So in this case, for example, I chose, if there's no variable, I chose S2 was in violation. I could only choose, I mean, X and Y are variables that I could have, X, Y, and Z are variables. If X was the only one that had a constraint, Y and Z does not have, but in general, if there is none of the variables, none of the non-basic variables can be adjusted, that is, can be increased or decreased to make S2 satisfy its violating bound, then that is when you will say it is unsat. Okay? So in this case, X happens to be the case. So you will declare unsat, you will look at all, if there's no, I mean, I explained the situation where you could have multiple choices to, multiple choices in the non-basic variable that you can choose to make the adjustment. But it is also possible that none of the variables you can pick to make them, to adjust the things to have them satisfy this. So then you will say unsat. Okay. Did that answer your question?
Yes, sir.
Yeah. So, and the way that you check is, okay, so it's getting late. Therefore, I will, I will kind of, stop here and then get to the actual procedure, which, with details that'll, give you things. So, yes, in the context of this thing, yeah, I mean, I guess an unsat situation will not have any intersecting points at all. The lines will be kind of running in parallel or something like that. Okay, that's what will happen. The set of possible extremities which can be a satisfying assignment, will be empty, and that's what happened. And in the context of this thing, before the pivot operation, you will have to pick a variable in order to adjust to make it satisfy. And the way that you do it is you will either have to be able to increase it. Okay, so the different way in which this variable can violate it is either its current assignment, based on the current assignment, if S2 can be violating if it is either less than its lower bound, or it is the value of S2 as per the current assignment is greater than its upper bound. Okay, both cannot happen simultaneously. So if it is lesser than the lower bound, the value of S2, then you pick a variable with positive, if it is positive coefficient, you will have to, if positive coefficient, you can pick a variable which has a positive coefficient, increase its current value, okay? Or if it is a negative coefficient, then you can maybe decrease its value to increase the value of S2 to meet its goal. That's how you check, okay, to do it. And if you can't find any of the variables to fix it, then you will declare unset. So yes, so I will stop here, modulo taking any questions that you might have. So next time on Friday, I will cover the actual algorithm, show some examples, show several examples, and also give you an intuition to the proof. I don't think I'm able to give a complete formal proof, which is described in the paper, and it's fairly easy. And it boils down to showing termination. Okay, that's all. Okay, I mean they reduce the problem of showing correctness to one of showing termination, and that itself is dependent on having doing the pivot operation as per an ordering on the variable. So I'll show several examples, 2 or 3 examples to show it, and also describe the algorithm in detail. Okay, any questions? Okay, if no questions, then I'll stop sharing.
Sir?
Yes.
So
So I had sent a mail. I wanted to discuss.
That's right. I did not forward to Madhukar and Hitarth. I want at least Madhukar and Hitarth to be there.
I did forward to them. That
Yeah.
said
So
that.
so let's discuss that. You hang on. So I'm not going to end the meeting here, but this is something logistics with Diganta and his teammate. So if the rest of you don't have any questions, you can take leave. Okay. Yeah. So I did not send that mail to Madhukar and Hitarth. So I wanted to be present. So, context, Madhukar, Hitarth is not here. He joined briefly. Uh, Diganta and your teammate is Shogata. Shogata is not here, no? No, no. Huh?
No, he's basically a little sick right now, so I couldn't attend to his class.
Yeah. So you can either do today. What is the nature of the question? Is it some that requires some technical thing? I mean, at length discussion.
So, sir,
I'm okay. I'm okay to stay, but Hitat is not there. So I'm wondering if we should do it when Hitat is also there. If there are questions about coding and implementation, then he may have a better idea. But otherwise, I'm willing to do it if Madhukar is willing to stick around.
Yeah, I'm fine with being around.
so
Yeah. Yeah. What is your preference, Niganta?
I'll just briefly discuss my situation with the project. So that is sort of what it is about.
Is it a sensitive situation?
And well,
No,
not
no. The reason I ask that is because there are two or three kinds of questions. Okay, I don't know which
okay.
kind. Technical questions. There are logistics questions, by which I mean, okay, I'm not even, or you're stuck at thing, or they could be personal questions, people related
No,
questions.
no, no, and it's not. It's nothing like that. It's not personal
Oh,
related.
okay, okay.
So I was I was hoping, like, I had some ideas about, like, coming up with this general framework for verifying this
Okay.
symmetry, right?
So
And
you
I mean, I tried a lot of things, but none of them really worked out as well as I would like at the end. And what I have right now is, I don't know how, like,
to
it.
proceed. Okay,
Yeah.
because we had conditioned it on. No, but I think at least part of it was um, yes. So now question is, if you did not, so you want to discuss that. So you're hit a dead end there. So you want to see if you did not do, you're not able to apply any of the ideas there to the system that we were doing. So what is it that what is the alternatives that we have? That's what we want to discuss.
No, so
Correct?
I have some ideas, but I don't think that, like, as in, I don't know if they'll be efficient enough is the question. So, or interesting enough as ideas in their own. The application towards the actual signal processing example, I think. I mean, at least in a theoretical level, I think I can see it being done, but I don't know if it will be efficient enough without any further standard abstractions.
Uh,
And I don't know if, like, I just wanted to describe what I had come up with and see if that would be enough for
okay.
the scope of the project.
So I have half an hour. Okay, not even 30 minutes. You can go ahead and discuss it. Does it require you to show us something, draw something?
I'll I guess I'll just share a Jamboard link and draw there if that is
Okay, let
fine.
me make you.
I don't think I'll need to be host. I'll just share a link onto a Google Jamboard, and that should be.
Okay.
So yeah, I'll make a new Jamboard.
So how are you sharing your?
I'm going to send a link in the chat, in this
Chat. Okay.
Yeah, okay. Is that fine, or should I send mails? I
No,
mean,
chat is fine with me.
okay.
You can see chat as well, no, Madhukar?
I'll send it to everyone. So
Yeah. I can see the chat. Also, I've uploaded the book.
Okay. Thanks.
Yeah. Yeah, you can check.
Oh, that was a oversight on my part.
Yeah. Even I'm sorry, I should have looked at. I had a copy myself, so whenever I had to consult, I just consulted my copy, so I never felt.
Well, that's what I do myself.
Yeah.
But somehow I had the impression that. Yeah. Anyway.
Yeah, I had just like when I knew the name, I just used some sites to download it.
So it's really there's several sites to download it from, is it?
Yeah, I don't know if they're like I mean they're not sort of any sites that want. I don't know how much like legal or whatever they are. I guess I have no other way of
I
putting
know.
it.
I mean, even this sharing is not sure.
I don't know about that, but there are sites. Yeah, I have shared a link, the Jamboard link. Is it?
Go
Can you
ahead.
open it, sir?
I can see it.
Yeah.
Madhukar?
Okay.
Yeah.
Okay. So basically, my basic idea was something like this. So if at any point we have like the neural network has got several layers, right? So this is a layer 1, and similarly over here we have some layer 2, and then layer 3, and so on. So if at any point this it happens that any like permutation of any two permutation of inputs under some permutation sigma becomes equal, say at this layer, then we are done. So that this is the
The
basic.
permutation, once again, to refresh my memory,
Yeah.
these permutations are not on structural properties, but on the input images, correct?
Yeah. So they are on. So a permutation would basically be, so if this is, say we are sending a vector, say x1, x2, and so on. An example would be something like, instead of sending this vector, we would send, say, a vector which would look like, say, if this goes up to xn.
Got it. Yeah. So it's not structural. Yeah. Now
It'll be it'll be x2, x3, and then so on up until xn, and then the last one would be x1, say. So something like this. So the property would be that this permutation is fixed, but the property would be universally quantified over all x1, xn. That is the idea. So what I was trying to find was basically, so basically my intuition was that, or the basic idea was that if it happens that, say even in the first layer, if it happens that after doing this permutation once, the weights of the first layer are such that at this stage, like the images of the two vectors under the first weight matrix, suppose, becomes equal, then we are done.
Mhm.
Right. So if that does not happen, then we can go on and check if it happens in the second layer, and so on. So my idea was basically this, that like we will
But that is, yeah, but that may not be the case, but yet your final thing might be equal. So suppose this flips and this flips again. I don't know if that will do. Theoretically, I'm saying.
Yeah. I mean, yeah, that'll there might be cases where, somewhere very like it only becomes equal at the very last node. Like that is sort of the worst possible case for us that I don't know if we can handle. But I mean, the also there's another idea that if says we check that in the first layer things are not equal, like under the weight matrix two permutations are not equal, then we can use SMT to generate some example of such x1, x2, xn, and then we can run that over the whole network and see that if that is actually a good counterexample or not. So basically the idea is what I want to do is at each stage, like pick one of these layers. Say we pick the first layer, and check if it is such that everything becomes equal, like any two permutations of this nature become equal at the first layer. If not, we'll get a counterexample, and then we propagate the counterexample forward through the network and check whether it is giving us two different results at the end. Then we have a counterexample to our property. But say if it's not a true counterexample, if it becomes a spurious counterexample, then we have to move on to the second layer and check, and so on and so forth. So this is the my idea. So essentially the way we are instead of having to do an SMT call involving all the variables for all the nodes of the network, we hope to do an SMT call only involving say the first layer or the first two layers or the first three layers to get like a counterexample. Of course, if it is like correct in a very non-trivial way, this will fail.
You will check if it is equal in the second layer. If so, you're done.
Yeah.
Not,
if it's not, then we have like a counterexample, and we check if that is spurious or not, and so on.
well, how do you check if it's spurious?
It's by actually like evaluating on the entire network. We don't use Z3 for that. Like,
but you will have to do it on all the counterexamples.
Yeah. So I mean that is another thing. So if we like, so for example, in the first layer, it is sort of like we'll get like say one counterexample or maybe two or three counterexamples, right? And then so we'll have to basically fix some number of counterexample for which we check whether or not that gives us a true counterexample or not. And at some point we'll have to give up trying to find a true counterexample for say the first layer and then move on to the second layer.
Can you say that again? I didn't quite get it.
Yeah, so basically suppose in the first layer we do find.
Can you repeat the last part that you said?
Yeah, that is what I'm repeating. Yeah. So if say in some layer, I'm just taking the example of the first layer. We do get some two things that are not equal in the first layer, right? Then
just hang on. So I need to do one thing.
Okay.
I need to stop the recording